Welcome to the video on section 5.2 in geometry. We are going to talk about incenters and centroids. So we are going to take some triangles, split them up again in different ways, and see what kind of amazing properties we'll discover. So that's what this section is all about. In section 5.1, we perpendicularly bisected some segments, and then we applied that in a triangle, and we bisected the sides of a triangle and found the properties that were created. Now we're going to focus on angles. So let's look at the angle bisector theorem. What happens when we bisect an angle? So I have bisected angle BAD with ray AM. If I've bisected that angle, notice angle A, both of these smaller angles are congruent, so it was bisected. A point lies on the angle bisector, like point M, if and only if it is equal distance from the two sides of the angle. So the distance, the length of BM has to be the same as the length of DM if it's an angle bisector. So this is a similar thing when we bisected a segment. Any point on that segment bisector was equal distant from the two endpoints. It's a similar type of idea here because things cut it exactly in half. It's on the angle bisector if it's equal distance from the sides. What you need to be careful of is when you measure a distance between two lines or between a point and a line, it always has to be the perpendicular distance. So that's why I drew these right angles here. If it is not the perpendicular distance, then it's not correct. So be careful. Don't let that trip you up in looking at diagrams. Okay, here is a rough sketch of a triangle, and I have bisected all three of its angles. So angle bisectors are concurrent at a point called the incenter. That point is called the incenter. The incenter is equal distance from the sides. So remember when I bisected the sides, the point where they met was equal distance from the three angles. If I bisect the three angles, the point where they meet, called the incenter, is equal distance from the three sides. That means that these three blue distances that I just drew in this triangle would all be equal. This one, and this one. That's why I made them perpendicular. Notice in doing that, I've also divided this triangle into several right triangles. So you're going to get some problems where you're going to be able to solve from angles and sides and lengths and this distances. You need to remember these three segments will always be equal if that's the incenter, if you've bisected the angles, and you've created some nice right triangles for some good problems. Now the reason that point of concurrency is called the incenter is because it's the center of the circle that's in the triangle. If you can remember it that way, that'll work. Obviously mine is very lopsided and crooked, but it was freehand drawn, and if it was actually accurate with a compass, it would look right. But those are the relationships that are created by bisecting the angles in a triangle. If you are given a triangle and are asked to construct the incenter using your compass and using your straight edge, then what you would do is bisect two of the angles and then connect those lines. So just to remind you about how to bisect an angle, you would take your compass and draw a little arc, and then from that opening you'd open up your compass and you'd make a little mark out in the middle from both sides, and where those little marks intersected you knew would be right in the middle. Then you take your straight edge and your pencil and you connect the vertex right through those points, and you would bisect the angle that way. I freehand sketched this, so it's not accurate, but that's how you would do the first one. then you'd repeat the process with either one of the other angles. And then the point they meet would be the in center, and it would look lots more accurate than my drawing here does. At that point, you should be able to open up your compass from that point of concurrency to any side, which would be the radius, and draw your circle, and it should just touch your 3 sides. Okay, let's divide a triangle another way. Now what we're going to do is find a median. A median is another new word. I hope you're putting all these different terms in your notebook, because there's an awful lot to keep track of, and having them in your notebook will be super helpful. So a median connects the midpoint of a side to the angle across from it. So this would be a midpoint. So those 2 segments would be equal, those 2, these, because these 3 are midpoints, and they go to the vertex of the other side. They have a point of concurrency as well. The point where they meet is called the centroid. Now, a centroid of a triangle has some pretty cool properties. If you take your triangle and you hold it up and you put the tip of your finger or the tip of a pencil or something right at that centroid and hold it up, it will be the perfect balancing point of your triangle. Doesn't matter if it's acute, right, obtuse, doesn't matter the shape or the size, that centroid is the perfect balancing point of the triangle, which is pretty cool in itself. It also, this centroid also divides these mid segments, not in half, but it does divide them. 1/3 of the median will be adjoining the side, the other 2/3 of the median attached to the vertex. So if you took this whole length, 1/3 of it is here, 2/3 of it is there. 1/3 to 2/3, 1/3 to 2/3. That's another way to learn a lot of different lengths. So I've just labeled this triangle, and now I've come up with a problem. If DC, the length from here to here, is 16, what would DX be? So this represents 2/3 of the entire line. This is 1/3 of the entire line. That means DC is twice as long as DX, because 2/3 is twice as big as 1/3. So if DC is 16, DX would have to be 8. So DX is 8, and CX, the entire length, would be 8 plus 16, or 24. That's what I meant about that relationship between 1/3 and 2/3. That it's consistent, always works every time, because God created it, and He is very orderly. Okay, another one. What if AY is 36? The distance from here to here, the entire median is 36. Then what would AD be, and what would DY be? Start by taking your length of 36 and dividing it into 3, because remember it's 1/3 and 2/3. So 1/3 of 36 is 12. So the shorter one, DY, would have to be 12, and then AD is twice that, or 24. 1/3, 2/3, the whole thing is 36. That's a consistent relationship with medians and centroids. Okay, we're going to find some lengths in triangle PRQ, knowing that G is the centroid. If G is the centroid, that means all 3 of these are medians. So if PD is 15, what would PG be? Based on the markings that I have here, what's RG and what's EG? Can you figure that out? So if PD is 15 and this centroid divides it 1/3 and 2/3, then the 2/3 of 15 would be 10. If this is a median and the short end is 3, then RG, or the long end, is twice that, or 6. Remember, 1/3 and 2/3 is a 1-to-2 ratio. If EQ is a median and GQ, the longer part, is 8, then EG, again 2-to-1, would have to be half of that, or 4. Once you get this relationship, it's pretty cool. Here's a review of all the different ways that we have bisected or taken triangles apart and the magical properties that we have discovered when we did so. So we talked about today what happens when we bisect the angles. The angle bisectors meet at the incenter, and the incenters are equal distance from the sides. We also talked today about the centroids. The centroids are created from the medians, and the medians are drawn by connecting the angles to the midpoint opposite the angle. And that centroid then is the point that divides those medians into thirds. 1/3 next to the side and 2/3 the longer part by the angles. And then the other lesson, or previously, we learned about the perpendicular bisectors meeting at the circumcenter, and the circumcenter is equal distant from the vertices, or from the angles. We divide the sides, our points equal distance from the angles. We bisect the angles, our point ends up being equal distance from the sides. If you keep that relationship straight, it makes it a lot simpler. And then the last one that we did was the orthocenter, which is just the point where all our altitudes meet. Nothing magical about an orthocenter, that's just what it's called. So those are the 4 different ways that we can divide up triangles. Some of them are more than one at the same time. You can have something be a median and an altitude, right? Those kind of things. So you might get problems that are related to that as well. For instance, can you tell me what CD is? Is it a perpendicular bisector? Is it an angle bisector? Is it a median, or is it an altitude? And if you look, it connects a vertex with, oh, look at these markings, with the midpoint across from it. So, there you go. So it would be a median. What about this one? What would FH be in this triangle? Oh, this is an isosceles triangle. So what would FH be? Well, if you look up here at angle F, you can see that we bisected that angle. So it's an angle bisector, which is cool. Also, because it's isosceles, we know that GH and EH are the same, so it's the perpendicular bisector. So it's also that. Oh, and it also connects the midpoint with the vertex across from it, so it is also a median. And it's also the perpendicular distance from one side to the vertex across from it, so it's also an altitude. This is all 4 in one when you have an isosceles triangle. So that's pretty cool. So that's what section 5.2 is all about, finishing up all these different ways to divide up triangles from 5.1 and 5.2 and putting it all together and keeping those relationships straight. I cannot emphasize a notebook enough, and then working with them until you get the idea. Also trying to find little hooks to help you to remember the different relationships. How do I remember it's an incenter or a circumcenter? All these terms are really easy to get mixed up in your head. So drawing pictures, whatever it takes to help you remember it. And that's all for this section. Hope this was helpful. I want it to be. I hope it was. And I'll see you guys next time.